Our next model is the water storage model. Very important, the crucial function of the wetlands to store water that we use for domestic use it for livestock and for irrigation. It's important to note that wetlands capture and store water, contributing to the quantifiable available water for subsistence and other domestic and commercial uses such as hydropower and such uses. Vegetation in wetlands acts as sponge, soaking up and storing water when abundant and releasing it slowly during the dry periods. Part of the water in wetlands filters into the ground and recharges underground aquifers. In the water storage model, the biophysical assessment is the volume of water in the wetland as the key indicator for the assessment. The model derives the water volume from various processes known to feed the water reservoirs, and these are the precipitation, the surface water inflow from incoming rivers, and surface runoff. This particular model also considers the starting storage of the reservoir at the start of the analysis period. The model also considers the potential water losses from the reservoir, incorporating evapotranspiration and surface outflows from the reservoir within the study period. The model allows for the segregation of total wetland volume to reflect the actual uses of the water for up to 3 uses. Example of uses may include domestic, irrigation, hydropower, and such kind of uses. This model is only applicable for reservoirs and lakes. In the economic assessment, we consider the direct market price as well as the avoided cost method, valuation techniques for the monetization of the quantified water volumes for identified individual site scale usages. So what are we saying in summary? We are saying that this model for the valuation of water storage as an ecosystem service from wetland considers the ecosystem service value to be equivalent to the prevailing market value of water stored in the wetland. In addition, it considers the ecosystem service value to be equivalent to the cost saved from using an alternative water source in the event that this particular wetland and assessment is rendered unproductive and the services no longer existed due to degradation. So what are the data requirements for this particular model? We have first the wetland raster, and then next would be the precipitation raster in millimeters per unit time. When you look at the guide, you can be able to see possible data sources for such data sets. We have the evapotranspiration raster in millimeters per unit time, totaled for the entire study period, starting storage volume of water in cubic meter measured at the start of the study period, surface water inflow of the wetland cubic meter totaled for the entire study period, surface water outflow of wetland in cubic meter totaled for the entire study period, volumes of individual water use percentages of total volume of wetland, unit cost of respective water use from the wetland, applicable currency per volume, unit cost of respective water use from an alternative water source. Remember, we said we have 2 types of assessment here, the direct market price and the avoided cost that would have been incurred if this wetland dried up and you moved to an alternative source. The feature area data in meter squared and the pixel area of the input rasters in meter squared. What are the technical considerations that you should have when you are looking at this wetland water storage model, or when you are trying to use it to analyze levels of water storage? The recommended data sources are found in the guide, the global and the national, that you can be able to apply for this particular model. But there are specific guidelines that are key, that following the requisite numeric data input, starting storage, surface water inflow, and surface water outflow are totally dependent on the availability of local expert knowledge. The model actualizes specialization to harmonize them with the wetland raster and the assessment. What are we trying to say in this case? In most of these reservoirs and lakes, you'd find the equipments that have been placed there to actually monitor surface water inflow and surface water outflow, and in most cases you find they can be able to gauge most of these measurements from the field. The alternative water source is an assumed water source that the water users are likely to resort to. So what you are trying to say, if, for example, we wake up today and find Lake Victoria has dried up, of course, we do not hope that will happen in the near future. What would be the next alternative source? How far would people have to go to get water? Would they have to go to Lake Tanganyika now that Lake Victoria is no longer reliable? Would people have in Kenya move from Lake Victoria and come all the way to Lake Baringo to find a water source? Those are the kind of alternative water sources that we try to imagine of our worst case scenario, which is likely to bring an added cost to the users, because if you are depending on a source that is next to you and it dries up, it means the alternative source is actually making you incur an extra cost to go there. So what we are saying is that it brings an added cost to the users if the wetland as assessment is rendered unproductive and the services no longer exist due to degradation, just like I've said. Finally, the numeric inputs depicting the water use percentages of water should not exceed 100, because, of course, if you are exceeding 100, it means you have already overexploited that available resource. So if you are having 4 or 3 uses, like I've said, if it's domestic, if it's irrigation, if it's hydropower, or if it's even for livestock, it should not exceed 100%. Finally, let us go to the model demonstration, input the data. Be in a position to run this model and then appreciate the kind of products that we'll be able to get. So this is how the water storage model should look like. We have our first data set there, the precipitation, the evapotranspiration raster, the wetland raster, the input starting storage volume, like we have said in most lakes and reservoirs, that is, you should acquire these volumes based on local knowledge, the input surface water inflow volumes, the input surface water outflow volumes. And then now you go to the percentage water uses, the 3 of them, and the unit cost that is attached to the 3, and the unit cost of assumed alternative water source, so that we can be able to say, supposedly now you are no longer able to utilize this water source. The alternative water source, what would be the unit cost? And of course, in most cases than not, it would be more expensive than the wetland area, the pixel, the unit cost of water. The second one is basically to do an assessment of whether there are changes based on the initial storage. Every wetland has its own capacity. Beyond that capacity, whether it is operating below the capacity where it is supposed to be operating, or maybe it has maintained that particular capacity. So the unit cost of water would remain the same for what was initially being factored in for the other uses for the wetland. And then you also put the maximum volume of water or the capacity of that wetland. And then finally, you identify the output folder where you want your products to be saved. So we input the data from the folder where I have saved it. We have the water storage model data. We are starting with the precipitation. We open, the next one is the evapotranspiration. The next one is the wetland raster, the landscape that is being assessed or being valued. So here we look at the starting storage. Let's say the starting storage of this wetland is 10 million metric cubic meter of water. 10 million, there's 1 0 left. What in input surface water inflow, maybe at one point we normally have around 10,000 meter cubic coming in. Input surface water flow, let's give it around 1,000, what is going out. These are figures that with local expert knowledge you can be able to find for that particular wetland. Then we look at the percentages. Let's say 10% is or even 30% is going towards domestic use. Then we have 10% maybe for livestock, and we have another 20% going towards irrigation. The unit cost can be distributed. Let's say it's 1,000 per cubic meter. It would be actually almost the same for most of these uses. the prices wouldn't change much. So for the alternative water source, we'll give it around 2,000. The wetland area we input based on the size of that landscape, and the pixel area is 900. The unit cost of water is the same as what was factored in for these uses, because we are trying to gauge whether there's a change in value based on the volume of water that is currently being stored in the wetland compared to the maximum volume of water that was there. Let's assume the maximum volume of water or the maximum capacity for this particular wetland is 12 million cubic meter. And then we identify where we want our data to be stored, so that once we run the model, we just go there and open the output. So we use the output data folder, and then once we have loaded all the data sets, ensure that everything is okay, then we can be able to run the model and allow it to run. So the model has finished, and we can actually go to QGIS and visualize the product. We now add our water storage output from the water storage model, from the output data folder, water storage. There we are. And that is our water storage value raster, indicating how much water, the value of the water stored within Kariba Dam based on the various uses assigned to it. So we can just give it a unique color. So and there we have it. So we'll be able to sum the water storage value raster to the flood control value raster to the water purification value raster, and we had the wetland products value raster, so that we can be able to see the summation totals of what we are likely to get, and then how does that inform decision making. Thank you.